All right, so we record and we'll pause and go back on. Here we are. This is episode number 2. We're going to talk about the tides. I don't really know what I'm going to talk about the next. I'll give you an idea, but I don't know. It's kind of what when I start looking, I have so many old slides and so many old. Since we're talking about gravity, I felt like we should talk about fundamental forces. We won't get a whole lot of Large Hadron Collider talk this time. Might be tomorrow. And standard model. We're mostly still coming at it from a gravity point of view, since gravity is really so important historically in physics. With the work of starting with Galileo and really Copernicus, but Galileo and then Newton, and then on and on, of course, Einstein. So gravity's been a running thread. So kind of a fundamental thing. If you know, the more you know about gravity and its research, the better you're off foundationally in physics. All right, so let's see what we got here. So tonight we'll talk about the schedule coming up. Payments and refunds. I've had some people have some trouble on. We're still figuring out Stripe. Stripe is the company we're using for our payments, but it's much simpler just to either drop by cash or a check, and for $30. That way you don't have to worry about any kind of service fee. And so if you haven't paid, that's the easiest way. $30 cash or check, and just bring it by 812 Carriage Lane. Now this will be, I take it back. There will be a video of this one, but this isn't the freebie. So this video will be available just by invitation. So like I'll have to send them, the people that missed tonight and I'll just send you all either in an email or probably in an email. I'll send you all the link to it. Maybe you could find it just by going to the website, but it's not searchable. It's one of those things. I don't want to make it totally private because that's really hard to find. All right. So the upcoming schedule is here. And like I say, it's a Monday, Tuesday, Thursday. I've been talking to Lloyd Baum, who's Dr. Baum, who's a professor at OU, about getting our physics buildings tour. And he's working out a thing where we would go like 15 minutes with one person, 15 minutes with another. And the whole thing would last hour to hour and a half or so. And it would be, I don't know what time of day, it probably wouldn't be 6:30 to 7:30. It would be, and it'd probably be the next week or the week after. We'll have to kind of work out a time. Probably not everybody can go, but I think with labs and all, they're only talking, they really don't want too many more than 10 students or student, even parent. But if we have room, brother and sis could come, but let's see how many people we have that sign up for it. Okay, and then we'll also work out, I would like to because it's hard to park around OU, so it'd be kind of cool if we parked at a park like by the firehouse, and then rode the bikes. You don't have to do that. You can just meet us there. But more about that details once we get that figured out. You guys feel free to chime in. I'll open up the chat. So feel free to ask a question or do it in the chat. And then as far as the Stevenson Research Center, I've emailed the professor that does it, and he hadn't got back to me yet, but I just did it this morning. So we'll figure out a time for that too. Okay, so talked about that. We'll do a little joke Monday. Then we're going to go over this 2D gravity problem that I gave you last time. I said, if you want to try one, and let's talk about that one, because that leads to center of mass and BaryCenters and all kinds of stuff involved with gravity. Then we'll talk about the 4 fundamental forces and some of the equations involved. We'll get into a little bit of string theory and gravophones, and maybe a possible reason why gravity is so weak in our universe. And then we'll do something with Earth and the Moon system with tides, because although we're not we're not coastal, tides still affect us. So I want to do some look at the physics of the Earth Moon system, and then we'll wrap up and preview what's going to happen tomorrow, what I think is going to happen tomorrow. Okay. So, and then don't forget, if you haven't already, most of you have there, join the Facebook group, subscribe to the YouTube channel. Also tomorrow, a little preview here, I'm going to interview Zach Burkett. Now this time I'll do it the smart way. I'm going to invite him to the Zoom. So he'll be like a guest and be like one of you, but then I can make it so that he can share his screen. It'll be like a 5, 6, 7 minute interview about what he does. Cause he just got his PE in civil transportation, which is civil engineering. But it's all this infrastructure bill they're talking about. He's going to have, trust me, this guy's going to have work till the day he dies. If you're looking for a job that you're never going to have any chance of ever losing, it would be civil transportation. And you get paid really well. So I'll have him, I'll interview him a little bit tomorrow during the show. Trying to keep the show a variety. Okay, so I'm going to push pause and do our Joke Monday. This Joke Monday is a classic. Nice cold bud. All right. Now back to work. Hopefully you heard that. But that's an exclusive only live special. Can't record those, copyright and such. All right. Back to work now. See if we can learn something. All right, so we are back to recording again. Yep. All right, so last time I gave you that problem as a suggested, attempt. And so I'm not going to give you, I'll give you one or two of those, but I think it's good to try. I mean, you can't learn physics just by listening to it. You have to try it. And then it helps me when I teach it. But I've worked this problem out. I don't want you to sit and watch me work it out. But I've worked it out. And so I want to talk about it. So it's the Newton's universal law of gravitation that big G M1 M2 over D squared, but now we have it in 2 dimensions. And so we have to use I roof and J roof. And Carson, I roof means basically X. You're going in the X direction, the vector, and J roof means you're going in the Y direction. If you have a third dimension, you call it K roof. But these are vectors are arrows. And so since the gravity is pulling on B, we're looking at what's the gravity on mass B. And so mass A is pulling on it gravitationally and mass C is pulling on it. And the question is, what's the result? So looking at the masses there, A is like 400 kilograms, which is like an 880 pound gorilla. B is 100 kilograms. That's about like a typical man at 220 pounds. And C is a child, about 110 pounds. So the question is, what is the gravity? And I realize when they're on Earth, gravitationally, they're not going to really attract each other. I mean, they are, but they're all stuck in the Earth's gravitational field. And so it's overwhelmed. But if they're out in space, they're going to end up rotating about this thing called a barycenter, but each one's going to put a gravitational force on the other. So I'm going to use this problem for 2 reasons. One, I'm going to show you the way you would find gravity in 2 dimensions. And 2, I want to talk about barycenters and centers of mass, okay, and orbits. And I have a great demonstration, which is at school. I just got back from Austin late yesterday, so haven't had a chance to get up there. But I'll get up to school, I'll pick up this demonstration, bring it back for tomorrow. All right, so here we do what's called stack and rack, where you put all the things that are in the x-axis, those go first, and that's our I roof. And then all the things in the y-axis, that's your J roof. And roof means this little, I think Max called it, they used to call it carrot hat. I think Max called it hat, but Walter Newman calls it roof. So for body A puts a gravitational force on body B, that gorilla on the man. And in that case, there is a X and a Y component. And so you're going to take the mass of each, which I have here, the mass of each, multiply those together. And then you divide that by the distance between them. And I look at the distance in the X. So 7 meters, -4 to 3. So distance squared. I made them both negative because if I'm calling to the left negative and down negative, B is being pulled to the left and down by A. And so in the J direction, once again, you put the two masses there on top in the numerator, then you square the distance between their centers, which in the Y direction is 5. The difference is 5. Okay. So then you're going to stack and rack. You're going to add that to whatever it is from C, the child. And so the child doesn't have anything in the X. It's directly to the south of B. So there's nothing east-west for the child. But he is far to the south. So it's 5 meters there. So you put in their two masses and then you divide by the square of that. When you add those all up, you get this for your I and J for the vector. So your force vector for both of them combined would look something like this. Now, when I first did it, I thought this red vector would be your force vector. When I first did it, I thought I made a mistake. And by the way, I kept it as capital G. We know that G is the universal gravitational constant, a really small number. When I multiply that, I get this for a force of gravity. And I mean, a Newton is a quarter pound. So we're looking at 10 to the -7th Newton. So this is not even detectable. It's so small. It's like if a gnat were to land on your arm, not even that. I mean, it's even less than that. So really, yes, there is an attraction, but gravity's so weak that it doesn't amount to much, but it would in outer space. So we'll get to that in a minute. So G is this crazy number, this gravitational constant, which as we talked about last time, they found at Cavendish. And you put that really small number in and you get that value. Okay. But I thought I made a mistake at first that this thing is being pulled to the south so much and not being pulled to the west because that big gorilla is to the west. You would think that B would be pulled more to the west. But when you look at it, hold on, gravity is an inverse square function, meaning that the further apart those two objects are, any two objects, the amount of gravitational attraction falls off as a square of the distance between them. So this is talking about items that are above the Earth. If you're sitting there, if you're at the Earth's radius, you're at typical gravity. 9.81 would be the acceleration, or 32.2 feet per second. But if you're twice as far out, it drops off. And this is the thing we talked about last time with the apple, right? And the reason why that apple kept dropping, to a fourth of its weight, to a ninth of its weight, to a 16th of its weight, is because of that inverse square law. This is the same thing with electromagnetism. When I do intensity on a flashlight and I pull the flashlight back from a wall, it fades very quickly. That's because it's inverse square. So electromagnetics and gravity are a lot alike. Okay, so back to this guy. So that's the reason why, even though the gorilla is much more massive, because it is 7 meters away rather than 5 meters away, that makes a big difference, and the gravitational attraction is dropped by quite a bit. Okay, now this brought up the idea of barycenters. The gravitational force vector makes more sense when you find the center of mass of those three masses. And that center of mass is called a barycenter, at least by astronomers. So if astronomers are looking at planets that are orbiting a star, or say two stars orbiting each other, or for a moon's Earth, say the moon and the Earth, or for a planet and its moons, they don't orbit the center of the planet. They actually orbit a barycenter. And there's a video I have. Okay, so there's a video I have that make sure, if you guys can't hear me, let me know, because I just got a note. Okay, your speaker has changed. Hold on. Okay, you guys can still hear me though. Okay, good. All right. So looking at this is the formula for center of mass, and we didn't really have time this year to go. I've mentioned it once. I gave you the Constantine story, and I said this is how he solves a lot of problems. And we could spend 2 or 3 episodes just working on center of mass stuff. But it's a real simple formula, and it's an easy way to find out what things will rotate about. So, like between those, going back to those 3 objects, in the X, if we consider A, the origin, and you have a choice as to what you want to consider the origin. I'm like, just make my life easier. I'm going to say that A, for my axis, I'm going to say that A is my origin. Okay, so that's 0, 0, the center of A. So if that's the case, I'm going to try and find out how far this center of between those 3 masses. Like if I were to throw, a lot of times you do this when you're talking about, say something you're going to throw, like a book or a, say you're going to throw something, throw a baseball bat. Okay. Then you look at where the center of mass of that baseball bat is, and that's the point at which that bat's going to orbit about or rotate about. So it's important, when you're dealing with anything that rotates, you deal with center of mass. All right. So anyway, we're talking about this case, we have 3 individual points, even though they have different masses. It's kind of weird. We're calling them points. It's a 400-pound point. This gorilla. This man is a 400-kilogram gorilla, 880-pound gorilla. That's a point. The man's 220 pounds, and he's a point. Okay, the child's a point. So we're doing it in the SI system in metrics, but so the reason why I say X is 0 is because I am calling that the origin. So it's 0. But what you do is you take how far it is from the origin, that's your X, and then the mass of the object. So this, whenever you see this little I here, it means maybe you know this from math class, but you can have X1, M1. This is like saying this. It's like saying X, oops, sorry. I don't mean to insult your intelligence. I'm not sure what you've learned in math class, but this is like X1, M1 plus X2, M2 plus X3, M3 divided by the total mass. Big capital M means total mass. All right. Whenever you see capital M in physics, it usually means total mass. Okay. So we look at this and we say, okay, well, that the big gorilla, the 400-kilogram object, is 0 meters away from itself. The 100-kilogram, that's the man, is 7 meters away in the X direction and 7 meters away and for both of them. The child is also 7 meters away from the gorilla. Okay, so then we divide it by the entire mass of the system. In this case, it'd be 550 kilograms. And you get 1.9 meters is the center of those 3 objects in the X direction. You do the same thing in the Y direction. This time you're just looking at the Y axis. And so you can see that the 220-pound man, the 100-kilogram man, is 5 meters away in the Y direction, and the child is 0 meters away in the Y direction. So you still divide that by 550 again, you get 0.91. So from the point A, from the gorilla, it is 1.9 meters over and 0.9 meters up, which translates in that coordinate system to negative 2.1, negative 2.1. So this X right there is the point at which those 3 objects would rotate about if they were out in space. That's the center of mass of the objects. If they were all connected with cables or say with beams and you threw the whole thing, that's what it would rotate about. But that's also what they would rotate about if they were out in space. So I want to show you a video. I'm going to share that screen again. I'm going to show you a video of this. Hold on. And I'll show part of it. And all these, if I don't show the whole thing, I'll put the link in the links there below. It's about a 3-minute video, and I guess we can watch the whole thing. But then I have a demonstration I want to show you as well, but I'll show you that next time when I get up to school and find that thing. Okay, so let's try that. Share that screen. All right, here we go. Hopefully there's no commercials on this one.
The moon is Earth's natural satellite. But does the moon really go around the Earth? Or does the Earth go around the moon? The answer is a mixture of both. With the Earth and the moon, they're actually both in orbit, around their common centre of mass. But what do we mean by that? These two tennis balls are of equal mass. Watch what happens when I throw them in the air. I've now got two more tennis balls, but with one big difference.
I'm going to pause the recording because I don't trust. Okay, so I didn't record any of that stuff, but anyway, so we were talking about the barycenter between the Earth and the Moon, and we said that that's actually not the center of the Earth; it's 1,000 kilometers below the surface of the Earth. And then we talked about Pluto and Charon, its main quote moon, and Charon doesn't really orbit Pluto; it orbits a barycenter between Pluto and Charon. Okay. So now let's talk a little bit more about these. There's a sheet in your material that it's if you kept your packet, it's in the packet. I think it's sheet 610. We did a couple things from there. Let me record this. Sorry, let me share the screen. We did a couple of things from there, but it's not important if you didn't share it or if you don't have it. But it's on the Facebook group if you want to get it and look at it. So when we actually do enough things from a sheet, I'll go ahead and put the sheet on there. But there's no really special curriculum with the physics show. We just come up with stuff, and I probably ought to come up with a way to see if you're learning it, but I probably will. But eventually, but right now we're just trying to feel our way through this, and I certainly welcome your suggestions. Okay, so when we talk about gravity, it's one of the four fundamental forces, and so you compare it to the well, let me show you. This has application to, let me go forward here. This is one of the slides from Dr. Strauss's talk, but if we're talking about the beginning, the Big Bang, the beginning of our universe. It's an old saying that more things happen in the first 1 second than has happened since, as far as fundamentals. So at the 10 to the negative 50th second after the Big Bang, that's a 0.49 zeros and a 1 seconds, all forces were combined. The grand unified theory, all forces were combined, including gravity. And then within 10 to the negative 40th seconds, there's a split between electroweak, strong went one way and gravity went another. Okay. And then at about 10 to the negative 30th seconds, the electroweak force split from strong force. Okay. And then at about 10 to the negative 10th seconds, which was an eternity, of course, time is relative, right? So back then, that's a whole epoch. But then electricity and the electromagnetic force and weak nuclear force split up. And so then at that point, from 10 to the negative 10th seconds onward, we've had four fundamental forces that we know of. Those are the only four forces. And those are still the same forces we have in our universe. So the first 1 second, the end of the first 1 second is right there. So look at all this stuff that was happening before that. And then after, it's just been those 4 forces. That's it. So not a whole lot. And then the 10 to the 20th seconds, or about 10 to the 18th seconds, is where we are now. That's the 13.6 billion years. Okay. So going back then to looking at these 4 fundamental forces, we should know a little more about them. The strong nuclear force is the strongest. If I say gravity gets a 1 or 10 to the 0 power, let's make that the base, and we know 10 to the 0 is 1. Then the weak nuclear force would be there at 10 to the 32nd, 10 to the 32nd. So it's 10 to the 30 times 1 with 32 zeros times bigger than gravity. Electromagnetism is a lot bigger than that. It's 10 to the 35th. It's 1,000 times stronger than the weak nuclear force. And then the strong nuclear force is 10 to the 37th times, so 100 times stronger than electromagnetism. I never understood in high school why protons, which are the same, I learned the protons were like charges, and I'd learned from my high school chemistry teacher that like charges repel. And then a couple of weeks later, we learned that the protons were all stuck inside the nucleus. And I asked why, if they're the strongest, if you have this positive repulsion, how can they possibly stick together? And she didn't have much to say about that, because I remember being frustrated. So we'll talk about that in a second. But gravity, then, the thing about strong nuclear force, extremely strong, but it's 10 to the negative 15th meters is its width. That's as far as it can go. It cannot reach out and grab you. It's all the strength in the universe, but itty bitty living space. So it doesn't go very far. Electromagnetism, on the other hand, it's Coulomb's law, and it's inverse square, but it is infinite. I mean, it drops off really quickly, but it is between a positive and a negative. If all you had is one positive, say it was in Dallas, and one negative in Norman, they would still feel each other, barely, but they would still feel a little tug between them. The weak nuclear that's beta decay. Of course, we need it. That's how the sun shines, but that's 10 to the negative 17th meters. Even smaller, it can't reach out and grab anybody. It's really tiny, small range. And of course, gravity is kind of what holds the whole Milky Way together, along with some dark matter, but it's infinite. Okay. The carriers there for strong nuclear is gluons. That's a very fitting word. For electromagnetism, it's photons. For weak is these thing called the W plus and W minus bosons. And then you have gravity, which is gravitons. Now, gravitons have not been found yet. We're still looking for them. Maybe somebody in your generation will find those gravitons. So here's another chart on that, showing what they act on, what they're carried by. I'll put that in the screenshots. Here's a really good, I have this link to this one. This is hyperphysics, and hyperphysics is one of the links you should have. I trust them. That has been vetted. All that information is good. So here's a much more detailed version of what I just said. It's probably something that you're going to hit in every physics class you take. They'll be talking about and chemistry. You might have heard this in chemistry, but there's more details of what I just said. And then, we talked about equations, and I was talking to Max about this, and I showed him the electromagnetics. He goes, yeah, I think I've seen some of those symbols. A lot of these are suitcases. So I want to get into it a little more, and I'll put a link to this right here in the comments. But let's talk about these forces a little bit more in the equations. Okay. So we start with strong nuclear, and hold on. You guys can see this. I'm sorry, my chat room. If I open up too many screens, my computer goes just kaplooey. That's unfortunate. I'm going to need a new computer. are on the money right now. All right, so here's strong nuclear force, and this is what I was saying to my 11th grade chemistry teacher, was that if electrons repel each other, that's called Coulomb repulsion. But what happens is, and she didn't really tell me this, what happens is it gets to a point of a femtometer. Now remember, a picometer is 10 to the negative 12th. When those protons get a femtometer apart, then the strong force takes over, and we get these. This is energy in something called electron volts, and it's a form of energy. It's electrons moving through a volt. It's a really weird way of doing it, but that's the way they do it in electromagnetics. And so I just realized it's kind of like the electromagnetism version of Newton's. All right. So, or really energy, sorry, joules, more of the electromagnetism version of joules. So it's called electron volts, and these are mega electron volts. But the thing is, the attractive force that electromagnetic well, like there's gravity wells, right? This well is it's an attraction force of the strong nuclear force. So it's a strong nuclear well that those protons fall into, and then you cannot break them apart. To get those to break apart requires chain reaction, requires fission, right? So we're talking nuclear bomb stuff. Force between protons, another thing. I'll add this to the screenshots, but just something I find, if you're into nuclear physics, they talk about that. And then as far as electromagnetism, the equations, these are the two different forms of Maxwell's equations. And I think next time or the time after, when I finally do get to work, we're going to go into integrals. We're going to look at integrals. And so there's a differential form, and that's like the derivative, right? Like little d, that's little d's cousin. That is right here. That is partial d. It's partial derivatives. Like if you have a big long function and you say, well, I just want to take the derivative with respect to t and not respect to x, then you do what's called a partial derivative. That's a curl. They're all special names for all these. These are all suitcases. A lot of these are suitcases. And so that upside down triangle is called the curl if it's cross products. And so it's kind of, this E is electromagnetic field, the B is a flux field or magnetic, sorry, the E is electric field, the B is a magnetic field. And these are called Maxwell's equations. And I'm just trying to show you that without going into it too much, is to show you that they got their dot off, it looks like. But to show you that, let me fix this. That dot should not be there. That dot should be, hold on. These are cross products and dot products. And maybe we'll get to a little bit of cross products and dot products. Cross products cause things to rotate. That's why it's called the curl. And then dot products gives things energy. It's where work comes from, and energy. So, and then there's the integral form of that. And it's the same idea, doing it this time from the integral point of view. So that's electromagnetics. And then the weak nuclear, there's all kinds of equations that go with it. But an example of it might be a proton turning into when a proton and neutron come together. Now, neutrons can spontaneously turn into protons, and that's called beta decay. And so that kind of stuff has to happen in the core of the sun, or we would never have what's called deuterium, and you would never have the fusion reaction. So the sun, any star, would not be able to light and give off heat without this weak nuclear force. So people don't talk about it much, but it's pretty important. This is a Feynman diagram showing a little bit of what's happening with weak nuclear forces. And then finally we get to gravity, and the one that I picked was Einstein's field equations, which is right here. And Einstein's field, once again, these are suitcases, right? If you open these up a little bit, you have something like this. And these are tensors. A vector is a form of a tensor, but we'll get into tensors. Tensors are described with matrices, And there's a guy named Daniel Flashman that put a lot of stuff out on this. Really, you have to understand tensors to figure out gravity. Um, this is one of my favorites, though. This left side of the general relativity equation tells gravitational space-time how to curve, and the right side tells matter how to move in that curvature. So it comes down to basically the G and the T. The G, the capital, this is not the same. This is not the universal gravitational constant. This, I don't know. I agree. They're using a capital G. I wish they didn't. But and plus it has to do with gravity. But this is an Einstein tensor. And that, like I say, describes the curvature. So if you want to put Einstein's equations on a t-shirt, this would be it. But you're putting some really big suitcases there. So that G is the Einstein tensor, and then that G is the actual universal gravitational constant. And then this T, the capital T, is this energy momentum tensor. And so tensors are three-dimensional. They're like three-dimensional vectors. But that shows how, this is the equation that shows how space-time curves. Okay, so obviously I'm throwing a bunch of equations at you. Here's a book that I want to show you. Hold on, let me stop this. This is one of my favorite books. I gave away a ton of books this year, and I'll give a ton away next year to kids. This is one book I didn't give away. Look how thin it is. It's called The Equations, Icons of Knowledge by Sander Bias. That's B-A-I-S, Sander Bias. And if you're looking for a good book, it's not hard to understand. Well, I mean, it's got a lot in there, but it goes into a tremendous amount without a whole lot of, even gets into ideal gas law, without, just boring you with tons and tons of equations. But it does talk about, like, here's the NAMBLA symbol I talked about, that curl. It does talk about Newton's laws as well. It has those equations, just simple rising and falling. It talks about terminal speeds, those kind of things. It gets into P is equal to mv, constantly momentum, Newton's laws, Newton's first, second, third law. It gets into all this stuff. It gets into ultimate fighting tool, which we'll talk about. But it goes into, it doesn't pull any punches. I mean, it goes into some tough equations. It even gets into kinetic theory, gets into Hamilton operators, it gets into Schrodinger's equation. Okay, so that's a really good book. If you just want to try and put all these equations you're going to be getting in the next 4 or 5 years into one little book to kind of go back to refer to, because sometimes it's important to step back, and you get so caught up in the, every little tree, you need to step back and look at the woods. Now, this guy here, his name's Daniel Fleisch. He is a gifted describer. And this is one of my favorite books, Student's Guide to Maxwell's Equations. He also has a student guide to vectors and tensors. I have not seen that book, but it looks excellent. There's also a student guide to Schrodinger's equation. So you're not going to worry about Schrodinger's equation until you're probably a junior in college, but there's one whole course built around one equation called Modern Physics. And then there's a good book here on Newton's laws of motion. The only book of these that I have 2 of these books. I have that one, and I have that one. I'd like to get all of them, but maybe eventually. Okay, so if you look at, my book recommendations. Okay, we talked about that. All right, and we got about 7 minutes left. I want to at least start talking about why gravity, one possible theory. Now, Einstein would say that gravity is so weak because it's not even a force, right? I mean, it's his equivalence principle that you cannot tell the difference between acceleration and the effects of acceleration and the effects of gravity. We went through this. If you want to look it up, just look up Einstein's happiest thought or Einstein's equivalence principle. And you should watch the Genius series on Einstein. They do a whole 10 minutes devoted to this in that series. That's what Einstein would say. He would say it's because of curvature of space-time, right? That's basically the higher the gravity, the steeper the slope of this curvature of space-time. what, and that's, people aren't arguing with that. But another interpretation of it is by this woman here. Let me share the screen for a second. I know we're running low on time, but by this woman right here, and maybe if it comes up, there it is. This woman right here, her name's Lisa Randall. I believe she's Harvard, yeah, one of those. She's written a number of books. She's a good writer. I've read a couple of her books. Um, she puts it into layman's terms, but she's one of the world's leading string theorists. And so strings are, that's way beyond any course we're going to do, but this is a physics show, so we can talk about anything. Strings are basically what everything is made up of. Now, don't think of it as cotton strings. When I first heard strings, I was thinking, you mean like strings? Like, no, they're like vibrating violin strings. So of a, say, woodwind, say an instrument, not a woodwind, but say a viola or a cello or something, a guitar, all these strings, and they have their characteristic vibrations. Okay. So the strings are what make up everything in the universe. Now, these things, we're on the order of Planck lengths. So we're on the order of 10 to the negative 34th meters, or really, we will never, I don't care how good our microscopes are, or electron microscopes or whatever we have, we will never, even scanning tunneling microscopes, which I think we're going to see one of those at OU, but we're never going to be at that size where we can see, quote, see, even perceive strings. That's the good thing and the bad thing about it. The good thing is, I mean, it's theory, right? No one's ever going to prove them wrong. The smallest particles basically are vibrating strings. And if you want to find some good stuff on this, look up Brian Greene on YouTube, or read Hidden Universe, or reading some of Brian Greene's stuff. He talks all about strings. He's a string theorist as well. And so there's two kinds this is what Lisa Randall's saying. There's two basic kinds of strings. There's open strings, which are attached to these brains. And the universe, our universe, is a brain. I don't mean like a brain, like your human brain. I mean like a membrane. And so these strings, these open strings, are attached, could be attached to the membrane, to the brain of our fabric of our universe, or they could be closed strings where they're not attached to our universe. Okay, keep that in mind. So there are some strings, looking at tries like are kind of three-dimensional. Some strings are attached. This yellow thing would be our universe. Some strings are attached to our universe. Some strings float because they're not attached. Keep going. Keep that thought. So there's another picture of that. Strings that are attached. Now, when I say strings, I mean like there's electromagnetism string. All these are different kinds of strings. So this brain theory, there's a strong nuclear force string. There's a weak nuclear force string. Then there's gravitational string, and here's what Lisa Randall says: the gravitational strings, these gravitons, are connected to themselves. So they're not connected to our universe, which means that here's a three-dimensional brain like our universe, but the open strings, the open strings are attached and are stuck. I promise you, I have not been doing psychedelic mushrooms. The open strings are attached. All these that make up our universe, all the things that make everything around you, are made of strings, and they're attached to our universe. But gravity strings, are not. So therefore, gravity strings can go between universes. And so the reason why gravity, as we showed way back on this previous slide, I know I'm almost done here, the reason why gravity is so small compared to strength is so small compared to strong electromagnetic and weak nuclear is because we're only getting a very small portion of gravity. Gravity is mostly shared, like, okay, so there's parallel universes. They're called parallel brains. Each universe is a brain. So gravity floats, these gravitons can float in between universes. And so therefore, the cool thing about that is that, and Lisa Randall talks about this, that if we could tap into this, one day we could have a graviphone where we could communicate with other universes, because that's the one thing that connects us are these closed gravitational strings. Well, I wanted to end on a big bang, and so I get it. I ended on a big bang. The idea of us communicating with other universes using graviphones, which takes advantage of closed gravitational strings. Okay. Well, you never know what we're going to talk about on the physics show. I was going to get to tides, and what tides are really cool because there's land tides and water tides. It's not just when the water rises and falls. There's all kinds of other things involved, physics involved between moons like Europa and Jupiter and our moon and moons being tidally locked. How does all that work? So we're going to talk about that. I promise you, we'll talk about that next time, and that'll wrap up any kind of gravitational stuff. And then I want to get more into machines, so I'm going to kind of come at that from a pulley setup. I have a table that came in, but I haven't put it together. It's going to take me forever to put that together. So I'm still trying to catch up with being gone from Austin and now working on taxes and cutting the yard, that kind of stuff. But I will get to the tides and tidal effects and tidally locked and earth moon systems next time, as well as pulleys and then energy and work, that kind of thing. Okay. Questions? Anybody got anything they want to say? Now you'll probably tell me that you couldn't hear a word. Well, you just sat there and watched me. Always, if you see something weird like that show, that thing we're watching, quickly get on there and wave at me or something. I can't always see the chat, but let me know that you can't see it so I can try and fix it. We're going to have some glitches. Okay. My thing is by August, no more glitches. All right. So you guys are ready to take off. I'm going to stop the recording.